All right, so continuing on with nucleophilic additions of alcohols onto aldehydes and ketones. In this video now we're going to concentrate on what happens when the alcohol that we use happens to have two hydroxy units. In other words, what happens when we deal with a diol. All right, so the reaction in essence is identical in terms of what happens step by step compared to the regular alcohol counterparts. Basically, you have to protonate your carbonyl molecule with acid if you're doing this under acidic conditions. This will, of course, generate your free diol molecule and your protonated carbonyl, which is now perfectly situated to react with a nucleophile. Now, in this case, the nucleophile is the diol itself. So this will be a reaction that you carry out under basically solvent conditions in which the solvent is, in fact, the nucleophile, right? So the diol is the solvent. So one oxygen of the diol will attack the carbonyl carbon, kicking the electrons back to the oxonium oxygen, producing the neutral hydroxyl unit. But now we have this oxonium cation for the part of the diol that did bind to the carbonyl carbon. So what happens in the next step is deprotonation, just like we saw before. And the deprotonation, can happen with a solvent molecule. Even the other oxygen of what used to be the diol can remove that proton to make this thing, neutral. All right, now what ends up happening now is that that proton is in essence getting shuffled from the oxygen that basically came from originally onto the hydroxyl oxygen, right? So that proton is now taken by the hydroxyl to protonate this into a water leaving group. And then notice once again throughout the entirety of all these steps, all the molecules, all the organic substrates are positively charged or neutral. But now in the presence of a good leaving group such as water, the very oxygen of that diol that is bound to the same carbon where the leaving group resides is going to proceed to attack by donating its electrons, forming a carbonyl bond in essence, but at the same time kicking away that water from the molecule. And now this is actually perfectly situated for further reactivity because the carbonyl that has been formed, which is part of an oxonium, component, is very electrophilic. And on top of that, we do have the second hydroxyl of the diol molecule that we started the whole process with, and it's like right there. So this next reaction happens like right away. Namely speaking, the oxygen of that hydroxyl attacks the carbonyl, kicking away the electrons back to the oxygen. And what now happens is that you have a ring. And when you guys do this, it's important that you count all your atoms, right? Like you're going to be attacking the carbon of the carbonyl, but that is connected to the oxygen, which is connected to the rest of the molecule, leading up to the second oxygen. So you want to count and say, okay, this is 1, 2, 3, 4, 5 second row elements. So you should end up with a 5-member ring. And the oxygen that did the nucleophilic attack, it still has its hydrogen bound to it. So that will give you 3 bonds on oxygen, making this positively charged. So the last event is the same thing you saw before. You have solvent or some other base remove that proton to give you the neutral molecule. And now the whole event that happened right here is that we went, and granted, this is all acidic conditions. It's important to point that out. Under acidic conditions, we went all the way to the acetal formation, right? We have formed an acetal, but in essence, the acetal is being made with the same molecule, a diol. And this actually serves a number of purposes. One of the main ones is that we can use this as a protecting group, because the moment that you trade a carbon double bond for two carbon oxygen single bonds, you no longer have the same reactivity that you will have with your typical aldehyde and ketones. So you could actually do chemistry that normally an aldehyde and a ketone would be completely incompatible with. And you can perform all those reactions under the presence of this diol protecting group. And at the end, you could remove the diol protecting group because, believe it or not, all the steps that I've shown you so far in the mechanism are fully reversible. So you can remove that leaving group under acidic conditions as well. So, and the mechanism will be basically the same thing, but backwards. You will start here, you will protonate your oxygen to end up here, and then you will make your way all the way back to the aldehyde. So this is something to keep in mind. If you do have a reaction that requires, let's say, a reduction, and you want to reduce an ester, but you happen to have an aldehyde also present in the molecule, protecting the aldehyde first by forming this acetal protecting group, and then carrying out the reduction of the ester, followed by removal of the protecting group, is a great choice, something to absolutely consider. All right, so with that in mind, we're going to stop the video right here. And on the next one, we'll talk about sulfur nucleophiles. And you'll see that at the end of the story, the reaction is almost copy and paste to what we've seen with oxygen. So I'll catch you in that next video. Bye-bye. Okay.